So in the prior videos we introduced slope fields, we talked about how to build a slope field from scratch. The discussion that we're about to have within this video is going to be, alright, well here are some slope fields that are already built. Which of these differential equations would have been used to build each of the slope fields? So matching up a slope field with its differential equation. On the AP exam in particular, it's easy to make a multiple choice question out of a situation like this. So it's definitely something I would expect you to see on that AP exam in May. So if we wanted to talk about how to do this, this is a one-to-one scenario that we have set up for the problems within this video. These four slope fields are going to match up one apiece with these four differential equations. Now here's one thing that I've seen people make some mistakes with in the past. Let's say that this slope field were shifted up one unit and that line that I just highlighted went through the origin rather than through a y-intercept of -1. I've seen people say, hey, dy dx equals x. Yeah, that's a graph of y equals x. That's going to match up with it. That's not the case. We're not looking to match up the solution that fits into the slope field. We're looking to match up the differential equation that was used to build the slope field, not the other way around. So you do have to pay attention to what you're trying to match up. Is it the solution that fits into the slope field? If that was the case, these would be listed as like y equals equations or f of x equals such and such, but that's not what we're doing here. We're trying to match up the differential equation that was used to build each of these slope fields. So my personal preference here is to look at where I have slopes that stand out. The slopes that stand out most frequently within a slope field or within the differential equation are going to be the places where the slope is 0. Like you can probably look at slope field A here and pretty clearly realize that right across, which was difficult for me to highlight, let me try that again, right across this horizontal, we have a sequence of 0 sloped segments. So what's true about all of those locations where I just highlighted? Well, x is definitely changing because I'm moving back and forth across the graph when I pass from this side of the graph to this side of the graph. But what's not changing is the y value. I'm not moving up or down at all. Looking at a y value of 0 on the x-axis and a y value of 1 across this diagonal, or across this horizontal, then this horizontal must be at a y value of 2. So it seems like my slope has to be 0 when y is equal to 2. Look at your derivatives. Do any of these derivatives have that property of always being equal to 0 when y is equal to 2? Well, this doesn't depend on y at all, so I can't really do anything with that. This depends on x and y. I might have to analyze that a little bit further. But then look at this one. If I put 2 in place of this y, because that's where these 0 slopes are, 2 minus 2 is 0. Regardless of what x is, this differential equation has a value of 0 when when y is equal to 2, and therefore what we're going to be able to claim is we're going to be able to claim that this slope field matches up with differential equation number 9. So we've got A matched up with 9. Let's move on to B. So if we look at slope field B, do you notice any places where you have 0 slope? Well, in this case, it looks like it's straight up and down the y-axis. What's true about all those points on the y-axis? All of those points on the y-axis have an x value of 0. Do any of my derivatives, do any of my differential equations have that property of being equal to 0 is equal to 0? So if you look at number 7, sine of 0. Well, sine of 0 is 0, so this has that property. This one here depends on x and y, so like we kind of said about choice A when we were trying to match it up a minute ago, that one we might have to analyze further, but we'll see if we can narrow it down without getting too involved with that first. This one, well, yeah, when x is equal to 0, this one's equal to 0. So it looks like we have two differential equations that have the potential to match up with this slope field because two differential equations have the property of being equal to 0 when x is 0. So now we have to look at other information. So the rest of the information that I like to look at is typically going to involve the sign, not the SIN, not this sign, but SIGN of my line segments. So I see that in my first quadrant here for this slope field, my slope is positive. In my first quadrant, x is positive. Does this have that property? Is this derivative going to be positive when x is positive? Yeah, for sure. Does this have that property? Well, sine of pi by 2, that's a positive number. Sine of pi by 2 is positive 1. But 3 pi by 2? 3 pi by 2 is also a positive number, and the sine of 3 pi by 2 is negative 1. So I'm not guaranteed that just because when my x value is positive, my slope is positive if this is the differential equation I'm using to build my slope field. But I think for this one, I am guaranteed to have that happen. Let's look at a little bit more information, since this one was a little bit more of a narrowing down process than that first one was. Look at all these slopes over here. It looks like if x is negative, my slope has to be negative. All of these slope segments here are negatively sloped. This has that property. If x is negative, the value of this derivative is clearly negative. If x is negative here, well, if I do sine of negative pi by 2, I get negative 1. But if I do sine of negative 3 pi by 2, that's positive 1. So this isn't always going to be negative if x is negative, but this one is. And that's pretty much the clincher here, so we'll get rid of that, and we will match up slope field B with differential equation number 10. So now we'll move on to these two at the bottom. So with number 7, or excuse me, with slope field C, and we've kind of already done the analysis here. We have the zero slope on the x-axis, excuse me, on the y-axis again. So when x is equal to 0, we have zero slope. This has that property. We just said that a few minutes back. We see that sometimes in the first quadrant we have positive slopes, but sometimes we have negative slopes. We argued that that's what's going to happen with this. Sometimes when x is positive, sine of x is positive. Sometimes when x is positive, sine of x is negative. When x is negative, sometimes the slope is negative, sometimes the slope is positive. This is definitely going to match up with slope field C. And then the final one, just through process of elimination, we know what the answer is, right? These are going to have to go together, but let's try to look for some evidence to confirm why. So look at where those zero slopes are for this one. They're down this diagonal. So what's true about that diagonal? Well, it looks like 0, 0's on that diagonal. It looks like 1, 1, 2, 2. So it looks like 1 minus 1, yeah, that gives me 0 slope. 2 minus 2, yeah, that gives me 0 slope. 3 minus 3, 4 minus 4, negative 1 minus negative 1. Yeah, all of those are going to work. So it looks like the zero slopes do correspond at these ordered pairs to when this differential equation is going to equal 0. We can look for other information if we had to narrow it down further, look for some positive slopes, negative slopes. In this case, we matched it up a little bit more quickly than that. Hopefully this is giving you an idea of a nice strategy to use if you're trying to match up a slope field with the differential equation that was used to build it.